Good morning, afternoon, I should say, left over from this morning's presentation. Thanks for joining us. Today, I'm going to spend a little bit of time talking to you about camshaft and valve train selection, how to pick the right valve train for your project. We're also going to talk about some new products, how they might benefit you in whatever particular project you're working on. So, when you're starting a project, you know, we're asking a generic question here: how to build a great engine? What's the first step? Just like building a house or anything else you do, or the rest of the car, you've got to have a clear goal in mind before you start. Okay. And we all have our favorite flavors, of course. But once you know your project, you have to define your goal. What does performance mean for your project? For a race car, it might be, you know, a high horsepower number. For a rock crawling vehicle, it might be really good off idle response. It might be fuel economy. It might be drivability. But before you start selecting parts for your engine, while you're making your plan, you've got to decide what's important to you or to your customer that you may be building a car for. Once you get this goal, you need to form a plan around it to make sure all the components work together to have the performance that you're looking for, and that all the components integrate, complement each other, and that none of them conflict with each other. Well, you hit on something: compromises, and that's what it's all about. With everything in life, there's a cost for every benefit, and the most important thing that we can do is to explain those compromises to you. Then the user has to make the choice: what's important to him, what does he mind sacrificing. You can never have your cake and eat it too. We would all like to think that. But what we can do is help you to make good compromises. And you want to lean all those towards the things that are the most important to you. I don't know a specific set of guidelines. There's a lot of publications, and there's a lot of things out there like that will help you define those, and we're going to go over a lot of them today. And by the way, anybody feel free to interrupt me and ask any question. The more interaction we have, the better this presentation is for all of us. So, as she said, I'm part of the Comp Performance group, and within our group, Comp Cams is obviously the leader of our group. We've got 6 other companies that fall within the umbrella of the Comp Performance group. So we're able to do cross-engineering between a lot of these brands, and it allows us to develop a lot of components that work well with each other. So I want to go over before we get started, a little bit of our engineering department, how we develop and design the parts and the products that we sell. This is a list of some of our engineering resources. We have 15 dedicated full-time research engineers that design, test, and develop products, full engine and chassis dynamometer, as well as Spintron fixtures for complete valve train dynamics. So what a Spintron is, for those of you that are not familiar with that machine, is basically it's an electric motor that drives a complete valve train up to very high RPMs with no pistons and rods. And we're able to analyze the valve movement, strain on all the parts, strain on push rods, strain on valve springs, high-speed camera recordings of valve spring movement. So we're able to learn a lot of things about packages. So this cam and lifter may work great with a titanium valve, but with a steel valve, it may have really bad harmonics. So we've learned things to avoid, and we've learned parts that complement themselves really well. And this is so the Spintron machine is critical in our valve train development. This is some of our engineering staff. It's a lovely bunch. So these are some of the pictures of some of the machines. We're able to machine camshaft cores on a CNC machine and produce a complete core from a billet bar stock. As you can see, what you see on the right is a high-speed camera image of a valve spring showing how much the spring, the retainer, and the dampener all rotate. You can see the white lines. There's actually a lot of movement going on, and that's normal. There's a lot more movement than we think going on when the engine's at operating speed. This is our banks of CNC cam grinders. By being able to program these, they're able to grind much more accurate and duplicate a lot better and hold tighter tolerances than manual grinders can. This is a picture of our R&D, or our QC department. On the left, you see the machine that says ADCOL at the top, and this is actually a machine that measures every aspect of the camshaft, run out on the journals, load profiles, and it's so sensitive, it'll read so far out, so many decimal places, that you have to use the cam mounted vertically, because if you do it horizontally, it'll measure sag in the camshaft. So this is a very, very accurate, very sensitive machine, and all our custom grinds go through this process before they're shipped.
Only custom grinds?
Some of the part number grinds, but as far as each cam, custom grinds, yes, sir. So this is a picture of our R&D shop, showing some of the different engines and equipment that we use. So this is a picture of the Spintron machine. This is a big block Ford Hemi-headed John Causey engine, and there's no crankshaft, there's only a mandrel that drives the valve train. But it has a full valve train, and we're able to spin it up at very, very high speeds that actually running an engine just wouldn't allow us to analyze what's going on. A couple of our test engines. There's a Coyote Ford 4-valve overhead cam engine on the left. On the right is one of the LS families of engines. You see the O2 bungs in the exhaust in the header, so we're checking individual O2 readings on every cylinder during dyno tests. Here's a couple more pictures of that's a 3-valve Ford on the left. I think the same engine on the right. It's a picture of a twin turbocharged engine. So, what we want to talk about for just a second is changes this decade, what we've seen change in the valve train world. More aggressive lobe designs. In other words, how quickly we're opening and closing the valves. Machines like the Spintron have allowed us to push the envelope of how quickly we can open and close the valve while still keeping it under control. Aggressive cam profiles are nothing new, but to be able to make them aggressive while not losing control of the valve train and without having harmonics that damage parts, that's where we're going, that's where we're moving ahead. Large cam cores, 55 millimeter, what we found is the bigger the journals, the bigger we can make the barrel, the cam is much stiffer. So if the cam's stiffer, it flexes less. You have less damage, you have more accurate control of the valves. Very stiff rocker arms and push rods. The use of strain gauges on push rods in the Spintron machine have allowed us to actually measure the deflection of the push rods while they're at very high RPMs, and it's taught us the value of really thick, stiff push rods. Actually, the additional weight is worth the extra weight to gain the stability. Wider use of lower mass valve springs, basically lightweight springs. And as you get the valve train more under control, you don't need as much spring pressure to control it. So less springs is less friction, everything's more under control. More.
Can you elaborate on that a little bit?
Well, basically, say...
How do you use less spring pressure to still control RPM and
one is the design of the springs. We're going to get into some really new spring designs that have really small diameter retainers. So most of the weight of the spring is at the base where it's not moving. The least weight of the spring is at the top where it's moving. Lighter weight valves, lighter weight retainers, locks, and also better materials for springs. Those things all allow you to use less spring pressure and control the valve, because the less weight you have on the tip of the valve, the less spring pressure you need to control it and keep it in contact with the lobe of the cam. And the profiles, absolutely. But it's critical that it's a system. For instance, the Sprint Cup teams are widely using this technology. And I'm sorry, I'm going to make sure everybody heard his question. He asked me to elaborate about how we could use less valve spring pressure and keep control. One of the things we use our Spintron for is teams will send us their engine, their block, their cylinder heads, their rocker arms, and ask us to analyze their exact combination. And if you change one piece out of that combination, it could completely go out of control. The spring that they use with their valve might not work with a larger diameter valve. It's a system. And our philosophy of treating as a system has allowed us to really move forward. And it's in Sprint Cup, for instance, durability is everything. The first thing you have to do to win a race is you have to finish the race. So without developing parts that make power and also have good durability, they're useless.
Some people in the industry talk about a variable rate spring. Do you guys work with anything like that?
Yeah, that's technology that we've used in some of our spring development, but basically the rate of the spring changes as it's compressed. And we've learned to put the right amount of rate in the right part of the compression. When it gets near full lift, that's when everything's moving the fastest and it needs the most pressure to control. Right off the seat doesn't necessarily need quite as much pressure. So, good questions. Good questions. So the question was, with a beehive spring, since you don't have a backup spring, basically if the spring fails, it's a total loss of control, whereas with a double spring, at least you have one spring still holding it. That was the question. So it's all about the application. OEMs, since about 96, all they use are beehive springs. But that's a stock vehicle. In a full race vehicle, there's not very many places I would say a beehive spring would be an appropriate choice. There are places where we use them in race vehicles, but for the
Where are you using the lighter springs?
lighter, well, like Cup, for instance.
We were just talking about using the lighter springs.
Mhm.
To use the lighter weight
Right.
on that side of the valve, and I understand all that, but how are you getting the lighter spring?
Well, part of it is the material of the spring and the diameter, the actual weight of the spring itself. This is,
Using smaller diameter weight?
that's part of it. They're using different shapes. They're using oval shaped wire. And also we've experimented with the profile of the retainers. Now we're using tool steel, which is a lot cheaper than titanium, but you can really cut down the amount of material. And by using computer analysis, we've been able to figure out where it needs to be thick and where it doesn't matter. And in the places where it doesn't matter, we're taking material out. So we're able to come up with a lot lighter retainer and even reducing maybe the overall outside diameter.
Do you get the tool steel retainer lighter than the titanium?
It's about equal for less than half the cost. Also, it has some benefits because titanium will gall over time and tool steel just doesn't do that. It's a lot more resilient and it lasts a lot longer. So titanium, if you put them side by side, might be slightly lighter, but in most cases, most of our customers are opting for the tool steel for the value. It's just a much better piece for, like I say, about half the cost.
Well, every grain say, you pick up 30 to 40 RPM.
No, I'm just in general. Just in general, if you take two identical pieces, tool steel versus tie, but the problem is tool steel, it wouldn't be the same piece. And for instance, see, we'll figure out how to put this. Because tool steel is so much stronger, we can make the piece smaller and be equally as strong as a titanium piece. So it's hard to compare two identical pieces because we would never make that. The tool steel, and we're going to carve more material out because it's stronger and we can. And that gets the weight really close to titanium. But if you want the absolute lightest, titanium is still the lightest thing available. Right, any other questions on springs? Okay. So other changes this decade, particularly in OEM applications, far more widespread use of overhead cam. We saw the 4-valve Ford engine in the picture a moment ago. That engine is very, very impressive as far as power output. It's a very close to stock engine can make 500 horsepower at the crank with 302 cubic inches. That's impressive. That's very impressive. This year's Engine Masters Challenge, there were 3 overhead valve engines, and they finish 1, 2, 3. So there's a lot of advantage to be found with overhead valve applications. Increased adaptation of variable valve timing. All the OEMs are using variable valve timing now, so you can retard the cam when it needs to be retarded and advance it when it needs to be advanced. You can gain a lot of mid-range torque with that. Not so much of a deal in a race application, but in street-driven or hot rods, there's some advantages to be found. And measuring of system stiffness. As we were talking about before with the Spintron, we're able to really measure how much things are flexing under actual engine operating conditions. And that's helped us to figure out where we can improve things. It's easy to just make push rods a lot thicker and bigger in diameter, or make rocker arms bigger and heavier, but that's really ineffective. We're looking how can we improve the strength and the stiffness while maintaining a good value and also being conscious of the weight. The question was, how are we dealing with the problem of stiffness in overhead cams? That's one of the benefits of overhead cams. There's no push rods. There's essentially no lifters. You're basically either pushing directly on the top of a valve or on a rocker arm. So stiffness really is not an issue in overhead cam. That's the big advantage of it. You've taken a lot of those pieces out of the chain, and high RPMs are achievable with 9,000 RPM with a completely stock valve train is not an issue. Specifically the Coyote Fords, I've dealt personally with a few of those, and 9,000, 9,500 RPMs and a stock eliminator engine is with stock rockers, stock lifters, obviously upgraded springs, but for the most part a stock valve train. So a couple of things, we got a new lobe catalog. Now there's a lot of lobe designs that weren't previously available to the public. They were only available for race teams. We've got a complete catalog now. Updated steel retainer profiles we were talking about. Basically, we've redesigned our retainers to get maximum strength with minimum weight for a good value. Yes, sir.
Are those new big steel retainers in the catalog yet? Or?
Yes, the question was, are the new tool steel retainers, and yes, they are in our catalog. Yeah, they actually, I guess the tool steel retainers were introduced SEMA before last, so yeah, they're definitely in our current catalog.
Designated as such in the catalog?
They are, and if you look at any of the retainers, it'll typically reference the tool steel equivalent. So if you're looking at titanium, it'll reference the tool steel equivalent. Continued expansion of the gold rockers. The gold aluminum rockers are a line that's done really well. It gives, for a good value, a good strong rocker arm. For the money, it's a really good piece. Short travel hydraulic roller lifters. That's what we were talking about earlier. These are hydraulic lifters that have minimum travel and they act more like a solid. And they complement very well with our aggressive hydraulic roller profiles. So it'll allow you basically to have a race engine with hydraulic lifters. So not only is you don't have to adjust them as often as you would a solid, but there's some real advantages to a hydraulic lifter right off the seat. A lot of people think solid roller is the ultimate race, and it is. And in the past, it's been the only way to get the duration and lift you want. But with a hydraulic, the lifter's always in contact with the cam. There's never any slack. With a solid, there has to be a part of the initial ramp that's smooth, so when it takes the lash up, it doesn't crash the valve train. With hydraulic, you don't need that, so you can actually get the valve open quicker right off the seat than you can with a solid. So there's some real performance advantages there. And the short travel lifter technology lets you take advantage of that. The 4-pattern camshaft. Oh, yes, sir. Yes, sir. Internally, instead of 50 or 60 thousandths, I think it's 10 to 20. And very little preload. We'll either run it at 0 preload just till the slack's taken out of the push rod, or maybe a maximum of 1/8 of a turn preload. And his question was about the short travel lifters. We're talking about the actual travel of the piston inside of the lifter. Okay, 4-pattern camshafts. These were These were introduced at SEMA. Actually won an engineering award at SEMA this year. Basically, so if you look at the manifold in the shot there, you can see that the two outer runners are obviously a good bit longer than the two inner runners. And for years we've done this where a cam is actually ground with different duration on the inboard cylinders versus the outboards. And race teams have done this for a long time because with the outboard runners, you need a little bit more duration to get equal cylinder filling because the air has longer to travel. So we call it a 4-pattern cam because when the cam is ground, they basically grind the 4 outboard lobes, the 4 outboard cylinders, and then they reset the machine and grind the 4 inboards.
We used to use different ratio rockers back in the day.
That's right. Same thing. It's exact same thing.
Are those patterns different for the exhaust side too?
No, because the exhaust, you've got a header basically, and hopefully the tubes are pretty equal in length. His question was if the exhaust lobes were spread, and the answer's no. It's strictly dealing with this intake design. So here's a better image of the longer path on a Chevy or Chrysler 1, 2, 7, and 8 half versus the inboard cylinders. And what we found is you can typically run a shorter duration cam. You could make an engine come in sooner and run out farther if the cylinders are balanced versus trying to make a compromise to make up for one or the other. So here's a picture. This is a graph that's got the O2 sensor readings. The blue cylinders are outer and the red are inner. And obviously you can see the outer cylinders are a lot leaner because in a carbureted application, less air, less fuel to the outer 4 corners. And you can see they get closer as they go, and that's as any engine approaches peak torque, everything kind of balances out. The cylinder, everything gets more efficient. You can see the outer ones go rich at the end, the inner cylinders go lean. So everything's just jumbled up. So by balancing it out, you can see that at the top we picked up some additional power and torque, and right at the very bottom it came in a little bit sooner. And overall, it regains overall. So the O2s, now this is a single plane intake manifold. So even though the O2s are still all over the place, there's no clear pattern. The outers and the inners are not favored one to the other anymore. So this is that was a dual plane. This is a single plane. And you can see the gains were substantial. Air fuel balance again. So here's a picture of the valve train movement. You've got your exhaust lobe, you got your intake lobe. The red line is piston travel. That's top dead center. So basically the overlap stays the same, but you can barely see that we've added the duration on the opening of the exhaust and the closing of the intake. So we've basically added it on the outside. The insides are exactly the same. Red line being inboard cylinders, blue line being outboard cylinders. So why use a 4-pattern camshaft? Better air fuel cylinder balance, 1 to 2% increased power for most manifolds. And what we found is the better the cylinder head, the more gains this allowed. Better response at low RPM, less fall off at high RPM, less sensitive to weather changes, easier to tune. And the ADCO machine I showed you, all the 4-pattern cams include an 8-cylinder report. So you actually get the report with that cam showing every cylinder's profile. So what took us so long to introduce 4-pattern cams? Even though we were doing it behind the scenes for years, most teams thought they were the only one that knew about this. But almost every cup team, a lot of the comp eliminator NHRA teams use this technology. But they're very difficult to grind because you've got to reset the machine twice. They're more complicated to run through QC because you've got, basically, it's like checking two different cams on one core. Any questions about 4-pattern cams? Okay. So this is the latest technology in valve spring. So we talked about the beehive springs earlier, and anybody that's not familiar with that, it's basically a spring that straight near the top, it rounds off, and it mimics the shape of a beehive. And it's not new technology. Beehive springs have been around for a long time. The newest technology is our conical spring. So it's got a consistent change in diameter from the bottom to the top. They're very difficult to wind. Basically, the production of these springs is very difficult because of the way the machines have to wind the springs, but we've developed technology that'll consistently produce spring shapes. So if you think about a pyramid, there's nothing more stable than the pyramid. All the mass is at the very bottom, no mass at the top. And that's the same thing we're going for here. The retainers are very small in diameter, so you don't need as much spring. Right now we're working on a dual conical spring for race applications. The frequency of the spring is better. Basically the harmonics, the high-speed camera footage of a spring at 10,000 RPMs is very stable as compared to a straight spring. The reduced mass gives you higher RPM stability, and also there's a super finish process that we use on the springs when they're done that gives them, it really increases the durability of the spring. It reduces the chance of a break or a failure in the spring. Anybody familiar with the new LT1 GM engine? It's direct injection. If you notice on this cam, the very back lobe is actually a triangle lobe. That drives the fuel pump on the direct injection. They operate at very high pressures. And we're the first ones to develop a core for this engine. We've also got 3 different options on the lobe of that pump. So if you want to increase the output of the fuel pump, since it's mechanically driven, it's controlled by the lobe. So we've got lobes that increase the fuel pump capacity up to 40%. These do require custom tuning because they do increase the output of the fuel pump. This is the first hot rod piece for the new LT1 Chevy engine. We can work with active fuel management and variable valve timing with this particular engine. And our new Sportsman series of solid roller lifters. We've basically got a good, a better, and a best on the lifter. We've got our elite race lifters. We've got our Endurex lifters that we've had for years and years with good success. This is a middle-of-the-road, great value lifter for the money. These are available with both needle bearings and with a bronze bushing on the axle. A lot of customers prefer the bronze bushing, a lot prefer the needle bearing, so we decided to offer both options. The lifter's lighter than the previous lifter. The axle's tool steel, so the axle's stronger, and it's got revised oiling there. It's actually pressure-fed oiling to both sides of the axle straight to the needles, because lack of oil to the needles is the most common cause of failure in a solid roller lifter.
You don't make those all in-house?
Yes, well, not in-house, but they're at a facility specifically for us. Any other questions about Sportsman lifters? All right, now the fun starts. What are the questions?